Lesson 23 is proving similarity in triangles using their sides. So 23.1 introduces two new triangle similarity theorems. The one on the left is the side-side-side similarity theorem. So I know that there's like a side-side-side congruence theorem. But that's really just to prove that the two triangles are like perfectly congruent, meaning their side lengths are all exactly the same. This is a little bit different in like the side-side-side similarity theorem is just showing that the side lengths are proportional. So if three side lengths or three sides in one triangle are proportional to the corresponding sides in another triangle, then the triangles are similar. So in order to figure out if two triangles are similar, we need to go ahead and just find the ratio between all of their sides. So in order to do that, we're going to use this kind of like setup right here. And it doesn't have to be like one triangle over another specifically. It's just helpful because you want to keep them kind of in the same order each time. So what I mean by that is if we're putting like triangle TUV in the numerator, we have to put it in the numerator every single time. And then triangle QRS goes in the denominator every single time. And of course you can switch them if you want to. It's entirely up to you. It just, whatever you kind of feel like would be better. Okay, so I'm going to set up just kind of the general like ratios without the actual side lengths. We need to kind of pair up all of the corresponding sides. So the first pair of corresponding sides we'll use is UV is corresponding to RS. So I'll say UV over RS. And then that's going to be equal to, or hopefully it's equal to, the next pair of corresponding sides, which we'll say UT is corresponding to RQ. And then is hopefully equal to the last pair of corresponding sides. So QS is corresponding to TV, or TV is corresponding to QS. So TV is over QS. And you don't necessarily have to do this like initial setup, but it is kind of helpful to see like the template that we're kind of going to actually put our numbers into. As you get more comfortable with these problems, I would say it's maybe something you could skip in the future. Okay, I'm going to shrink this down a little bit just to have a little bit more space, and then we'll go ahead and like actually putting in the values. So UV is 3.9, that'll go here. So 3.9. And then the next one is RS, that's 7.8, so it's over 7.8. And then that should be equal to UT. UT was 2.9. And then that should be over RQ, which RQ was 5.8. And then that should be equal to TV should be next. So TV was 2 over QS, which was 4. Okay, and then now we just want to actually like simplify them all down to kind of like either simplified fraction, or you can do a decimal if you want. It's entirely up to you. Probably kind of depends on the number of values you're dealing with. So like if you want, you can try to reduce these. I'm just going to change them to decimal form because I feel like trying to reduce a fraction with decimals is sometimes okay and sometimes just kind of meh. So the first fraction is 3.9 over 7.8, so that'll be 3.9 divided by 7.8, which is 0.5. And then the second one, 2.9 over or divided by 5.8 is also 0.5. And then the third one, 2 over 4 is 1/2, which is also 0.5. Okay, so we have we've set up our proportions, we set them all equal to each other, and it was true. All of the ratios between all the sides ended up being 0.5 or 1/2, depending on how you simplified. So as long as all of the side ratios are the same, that means that all the sides are proportional to each other, so we can say they're similar. So then the final similarity statement would be triangle, and we want to make sure we're careful with the order. The first triangle doesn't matter how we order it, so we'll say QRS is similar to triangle, and then we just want to make sure we go in like corresponding order. So Q was first, so T will be first, and then R was second, so U will be second, and then S was third, so V will be third. So TUV. So triangle QRS is congruent to triangle TUV. And then the second new theorem for today is the side angle side similarity theorem. So if two sides of one triangle are proportional to the corresponding sides of another triangle and the included angles are congruent, then the triangles are similar. So this time we only have like kind of two sides to show are equal, so we'll kind of match up our corresponding sides. So we want to show that, let's say, I'm going to start with like the blue triangle this time and do that on top. So I'm going to say AB is corresponding with KL, so AB over KL, and then that should be equal to the ratio between the other two sides that we know. So AC, keeping like the blue triangle on top this time, AC is over the corresponding side on the red triangle, which is KM. And then we just want to actually put the values in and make sure they are equal, and then we'll confirm the angle thing after. Okay, so AB, that is 5.8. And then over KL, that's 2.9. And then for the other ratio was AC, which was 4, over KM, which was 2. And then now we can just simplify each of these ratios. 5.8 divided by 2.9 is 2, and then 4 divided by 2 is also 2. So that just confirms that the sides are proportional because their ratios were equal. If you got to the point where like they weren't equal, then you would say that they're not proportional, but they end up being equal, just like in the first kind of problem we went through. And I know, so maybe you noticed, maybe you didn't. These are the same two triangles, essentially. Like, these two examples have the same two triangles, same side lengths and stuff. With the second example, we just flipped the way that we ordered our ratio. So, like, in the first one, we did red over blue, like right here. In the second one, we ended up doing the blue sides over the red sides, and that's why the ratio ended up being kind of the reciprocal of the original one. So the original was 0.5, which is like 1/2. This one ended up being 2. So just like the opposite of it, or the reciprocal of it. Okay, and then the last thing we need to check, so we just did this first part. So if two sides of one triangle are proportional to the corresponding sides of another triangle, and then now we need to cover the second part, and the included angles are congruent. So we look at the included angles, that's like the angle that's between the two sides. So that's A and then K. So since they both have like the angle line with the 1 tick mark, that means that they are congruent. So angle A is congruent to angle K. So it meets both the criteria. It has two pairs of sides that are corresponding and proportional, and then it has a pair, or it has the included angle that is is congruent in both. That was like a tongue twister almost. Okay, so since it meets both the criteria for that, we can go ahead and say that the two triangles are congruent. They have different lettering on this one, so it'll be a little bit different. So we'll say triangle A, B, C. And then just want to make sure that I match everything up right. So I wrote A first, and that corresponds with K. So when I write the second one, I'll say it's similar to triangle K. And then B was second, so that corresponds with L, so K, L. And then C was third, and that corresponds with M, so K, L, M. So triangle ABC is similar to triangle KLM. Okay, so just like two new theorems. These are in addition to the angle-angle similarity theorem, so there's 3 so far for similarity between triangles. I would like kind of keep them somewhere handy where you can go back and refer to them. So example 1, triangle ABC is similar to triangle KLM. What is the measure of CA, segment CA? So it's already confirmed that they are similar. We don't have to prove that necessarily. So if we know that they're similar, we know that all of their side lengths are proportional. So we just need to find the scale factor between like one set of corresponding sides. So whichever like pair of sides that you recognize as corresponding the soonest, just go with that one. So when I look at these two triangles, one is definitely flipped, but you can kind of tell what the long side is on each of them. And it looks like on the big triangle, it's BC is like the long side, and then LM is the long side on the short triangle. So to go from the short triangle to the large triangle, we're multiplying by 2. Okay, so like 4 times 2 is 8. If you didn't pick those sides as your corresponding sides, you could use AB and KL. And then the same thing there, like AB is 4, KL is 2. So to get from KL to AB, you would be multiplying by 2 because 2 times 2 is 4. So it doesn't matter what pair of sides you pick because it's given to us that the two triangles are similar. So that means that all the sides should be proportional. So we don't need to do the full setup here. We just need to identify the scale factor and how they're proportional, and then use that scale factor in order to find the missing side length. So the scale factor is 2. So then if I want to find that missing side, we have KM, and that corresponds with AC. So I just need to take KM, which is 2.5, and multiply it by 2. And that'll tell me that AC is 5. I said AC, but order's okay. So CA or AC, however you want to write it, is 5. Okay, so as soon as you know that the triangles are similar, you don't need to do like the full setup with all 3 sides, setting them proportional. You just need to find what the scale factor is and use that scale factor to find the missing value. Okay, moving to example 2. Is it possible to show that triangle ABC is similar to triangle DEF using the side angle side similarity theorem? So just basically, do we have enough information? So side angle side, we have 2 sides and we have the included angle. So the first thing that pops up to me is that we have 2 right angles. So that could be our like included angle. So then now let's look at the sides that kind of like close that angle in. So there's kind of like a short side next to the right angle. That would be in the smaller triangle, it's BC. And then in the larger triangle, it's EF. And then in the like kind of longer leg of each triangle, in the smaller triangle, it's AC. And then in the larger triangle, it's DF. So we just need to find those ratios and make sure they're equal. If you do it in your head, that's totally fine. Like, I'm just going to show you how to set it up, especially if it's helpful to know how to set up in case you ever deal with numbers that are more difficult in your head. So I'm going to do smaller triangle over larger triangle. So we'll start with the pink side. So in the smaller triangle, it's BC over EF in the larger triangle. And then that should be equal to, we'll do the green sides next. We'll say AC. It's the green side in the smaller triangle over DF in the larger triangle. And then now I can go ahead and put those actual values in now that I have it set up. So let's see, BC, that's right here, that's 6. So 6 over EF, which is 18. And then next is AC, which is 10. And then next is DF, which is 30. And then now we can simplify each. So each of these fractions can be reduced. You can divide if you want to. But if I wanted to reduce the first fraction, I would divide numerator and denominator by 6, and that would become 1/3. And then if I were to reduce the second fraction, divide numerator and denominator by 10, because that's the common factor. 10 divided by 10 is 1, 30 divided by 10, 3. So I end up with 1/3 equals 1/3. The ratios of their side lengths are equal, so these triangles' side lengths are proportional, which means that they are similar. So yes, we have enough information. I'm just going to say yes, triangle ABC is similar to triangle DEF. Okay, so show as much or as little work as you need to. Just like I said, if there's ever like something that you're having a hard time figuring out in your head, know that there is kind of like a concrete way to set it up that you can fall back on if necessary. (23.2) is using those 2 theorems we just talked about, side, 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 and side, angle, side, theorems of similarity in proofs. So given that AB is 5, CD is equal to 5, DA is 11, and BC is also 11, and we want to prove that triangle ABD is congruent to triangle CDB. So basically the bottom triangle is congruent to that top triangle. And then before we begin the proof, we want to kind of like look at, okay, what do we have? So what theorem are we most likely going to end up using? So there's 3 that we've learned so far, and the first one was in the previous lesson. It was angle-angle similarity theorem, and we don't know any angles from this figure, so we're probably not going to use this one. And then the 2 today are side, side, side. The second one is side, angle, side, and again, we don't know any angles here. I don't really see a way of us being able to figure them out, so we'll probably nix both the angle options and focus on the side, side, side. So we already have 2 pairs of sides that we know are equal to each other, like the 2 5s and the 2 11s. And then looking at the figure, we have, it looks like the third side is a shared side. So we know that that's going to be the same length. We'll just have to show it in a proof. So we always start with whatever is given to us. So AB is equal to 5, CD is equal to 5, DA is equal to 11, and then BC is equal to 11 meters as well. And then the reason is that's given. And then if we're trying to show that a triangle or 2 triangles are similar using this theorem, I'm going to go back up to the original theorem up here. So in this section, we showed that all of their ratios were equal. So if they're similar, then the ratio of all of their sides should all be equal to each other, all 3 corresponding pairs. So that's what we have to show here, is that all 3 pairs of corresponding sides, their ratios are equal to each other. So first we just have to find the ratios of at least the sides that we know. So we'll pair up the sides that are corresponding. So AB and CD, those are corresponding. So we'll say AB over CD, that'll be 1 ratio. AB is 5 and CD is 5 as well. And then 5 over 5 simplifies to 1. And then we want to find the second pair of corresponding sides that are hopefully to have the same proportion as the first one that we find, of the same ratio. So the second pair is DA and BC. So for the second ratio, DA over BC, DA is 11, and then BC was 11 as well, and then 11 over 11 simplifies to 1. So far so good, because they both have the same exact ratio. They both ended up being 1. And then for the reason, like, we didn't really use a theorem there. We just essentially, like, did math. So what did we do? We found the ratio of the corresponding sides. So for our reasons, we'll say ratios of corresponding sides. And then now we just need to find the third side. So we have 2 pairs of corresponding sides. We've proved that those ratios are the same. We're just missing that third side. So we need to go ahead and find that. The third side is the shared side though. So it's, BD. So if we want to find the ratio of BD to BD, that's how we can set up our ratio. So BD over BD. Well, anything, even if we don't know the length, like to put in for BD, which we don't, anything over itself, anything divided by itself is 1. So that ratio is 1 as well. So we figured out that all 3 of their ratios are congruent, so we're not congruent, but equal to each other. So we're on the right track. So for the reason for this one, it's basically the same as 2. All we did was find the ratio. So that's our reason, like that's what we did. So ratio of corresponding sides And then now for 4, we just need to kind of create a statement that shows all of their ratios are equal to each other. So we know we got 1 for each of them. So if they're all equal to 1, then they must all be equal to each other. So we can say AB over CD, that was the first ratio, is equal to the second one. So I got my first one. It's equal to my second one, DA. And this order doesn't like necessarily matter which one you make first and second, but DA over BC, and then the third, that's equal to BD over BD. So BD over BD, So since they were all equal to the same exact number, 1, we can say that they're all equal to each other, and that's called the transitive property of equality. So for a reason, it'll be the transitive property of equality. And then the transitive property in like kind of short term says that if x is equal to y and then y equals z, then x must also equal z. It just kind of like bridges the gap between like 3 equal values. Okay, and then now that we've said all of their proportions are equal, that's enough to say that the 2 triangles are congruent. So we can say, and remember, our finishing statement should always be like what we're trying to prove. So triangle ABD is similar to triangle CDB. And the reason is the side-side-side similarity theorem, because we proved that all 3 sides had proportions or ratios that were equal to each other. So side, 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 similarity theorem. Okay, moving down to 23.3, problem solving with similar triangles. So before we get into the actual examples, this is just kind of like a fact that can help us figure out some real life examples. So in this first section, triangle similarity, can frequently be used in real life situations. One of the ways to find the height of an object that is outdoors is by comparing shadows. An angle made by an object's height and its shadow is a right angle. So like if you're standing and then your shadow is like against the ground, that's a right angle, like you against the ground. Also, if the objects are relatively close to one another, like within the same city, and they're measured at the same time, the sun is going to reach them at the same angle. So the angle between like the object and their shadow, like if it's a person or like a tree or something, that's always a right angle. And then that second angle that they're talking about where it says also if the objects are relatively close, they are measured at the same time, the sun is going to reach them at the same angle. That's referring to like this angle, like the angle the sun is off of the top of the object. Okay, so because of that, we like can kind of create 2 similar triangles, because this goes back to the previous lesson, the angle-angle similarity. So moving down to this next little section, because the triangles have 2 congruent angles, the right angle and the angle the sun creates, they are similar. Because they have 2 congruent angles, that's all we need for the angle-angle similarity theorem. So we have 2 congruent triangles, and then that kind of helps us problem solve in more like real life situations. So moving down. So example 1, Kristen thinks the saguaro cactus in her front yard is about 15 feet tall, and her mother thinks that it's closer to 25 feet tall. They decided to find the height of the cactus. Kristen is 5 feet 6 inches tall, and her shadow is 2 feet long. At the same time of day, the shadow of the cactus is 8 feet long. Find DE, which is the height of the cactus. So because they are close together, like kind of in the same general area, and it's the same type of day, we know that the angle that the sun makes with kind of the top of the object, whether it's the cactus or Kristen, it makes the same angle. So if the sun is, say, like up here, that means that angle D and angle A are congruent. And we know that angle B and angle E are both right angles, so those are congruent as well. So if you have 2 angles that are congruent and like 2 pairs of corresponding angles that are congruent in 2 different triangles, that means that they're similar. You just need 2 in terms of angles. That goes back to, like I said, a previous lesson, like the one right before this. So we know that the 2 triangles are similar, like that's confirmed. Because they're similar, we can use that knowledge to figure out what the missing length is, which is the height of the cactus. So they're similar, which means they'll have proportional sides. So we just need to find that ratio. So I think it's pretty quick to find the ratio because BC is 2 and then EF is 8. So that means to go from, Kristen's triangle to the cactus triangle, you just have to multiply by 4. That's the scale factor that's taking you from the smaller triangle to the larger triangle. What's kind of a little bit iffy is that like Kristen's height is written in like feet and inches, so it's a little bit easier if we just go ahead and convert everything to inches, and then we can convert it back at the end. It's kind of tricky to like, you can, but it's kind of tricky to take her height as is and multiply it by 4, because then you just end up with like a lot of inches on there and have to convert it to feet anyways. Okay, so we can take Kristen's height, which is 5 feet 6 inches, and then just convert that whole thing to inches. So feet is like every foot there's 12 inches. So this, if we wanted to convert this to inches, it would be 5 times 12. So that means that 5 feet is the same thing as 60 inches. And then we'd have to add the other 6 inches because she's 5'6". So 60 plus 6 is 66 inches. So I'm gonna just go ahead and cross out the 5'6" inches and just write 66 inches. And then from there, now we can take that and we can use the ratio that we figured out, the scale factor that we figured out, and find DE. Because to get from one side to the other, like the smaller triangle to the larger, I just need to multiply by 4. So if I take 66 and I multiply it by 4, that's going to give me DE. So I can say DE is equal to 66 inches times 4. So 66 times 4 is 264 inches. And then if you were to like describe the height of something, you would never really say, well, 264 inches. Like that means like nothing, not nothing, but like not that much to the normal person. So we do want to convert it back to feet. So we'd say 264. If I want to convert it back to feet, I have to kind of think backwards. Instead of multiplying by 12, I have to divide by 12. So I would take 264 inches, and I can just divide it by 12, or you can kind of create like, in chemistry, you do these like conversion factor things. So what that looks like is if you have 264 inches and you want to convert to feet, you would say 1 foot is 12 inches. And the conversion factor, you want to like make sure that, you know, if inches is in the like numerator up here, or there's no fraction in general, it's in the denominator down here, and then that way the units cancel out. You'll do that a lot more if you haven't already once you get to chemistry, sorry. So 264, we need 264 divided by 12, because we can kind of like cross cancel, the inches cancel out. And then 264 divided by 12 is 22. And then 22 times, actually I'm going to write that over here. We can cross cancel. So if we divide both by 12, the 12 would become a 1, and the 264 would become a 22. And then I can take that 22 and I can multiply it by that unit 1 foot. So it'd be 22 feet is the height of the cactus. Okay, so you don't have to like do this full like kind of conversion setup necessarily. It was just something I wanted to throw in there to kind of make the connection or build the connection if you haven't taken chem yet. So just maybe once you take it, if you recognize it, it makes it a little bit easier. But anytime you want to go, this is just in general, it's a helpful thing to know. So if you want to go feet to inches, you would have to take the feet and multiply it by 12. And if you want to go inches to feet, you would have to go inches divided by 12, because you're just going in the opposite direction. So either way, 264 divided by 12, 264 inches divided by 12 gives us 22 feet. So I would say the mom was closer. Okay, so if you feel like you got enough from this lesson to be successful here, you can stop the video at this point. I'm going to go over this last example though, but just know if you feel good to go, you don't necessarily have to watch it. Okay, example 2, find the missing measurement. There was a whole word problem in the workbook, but didn't really want to deal with it, so we'll just use the graphic. So in this graphic, it's not guaranteed that these are similar. We have to kind of like make sure that they're similar. So to do that, first thing that pops out to me is we have vertical angles. So vertical angles right here, and those are always congruent to each other. And then we know the sides that surround them. So we know like this side right here is corresponding with that side, and then we know this side is corresponding with this side. So if we can prove that those two pairs of corresponding sides are proportional, then we can use that side angle side similarity theorem to say that the two triangles are similar, and then use that to find the missing side length. But we have to do like a little bit of work first because we don't know for sure if they're similar. So we know for sure that the two angles are congruent. So we're using side angle side. We have the angle, so we're good there. And then now we need to show that the two side lengths, two pairs of side lengths are congruent. I'm gonna use like larger triangle over smaller triangle. Side lengths, you can do smaller over larger, it doesn't really matter. So we'll start with the pink sides. So the pink side on the larger triangle, that's the one on top, is 1,200 feet. And then the pink side on the smaller triangle is 800 feet. And then we'll set that equal to the ratio of the green sides. So on the large triangle, the one on top, the green side is 1,921 feet. And then on the smaller one, it's 1,280 and 2/3, which is kind of rude, feet. But so 1,280 and 2/3 is kind of a doozy, because 2/3 is like a decimal that doesn't terminate, so we can't really change it to decimal form, which is unfortunate. So we'll just have to kind of simplify it piece by piece, which is okay. So what I'm going to do is just go ahead and get the like 1,200 over 800 simplified, so we can just divide those. So if I divide those, that's 1.5. Okay, so that's good. Now I just have to take the like green ratio and like make sure that also equals 1.5, and that's going to be a little bit more difficult. So one thing I'm going to do is I'm going to change the 1,280 and 2/3 to an improper fraction. Like I said, we just can't really change it to a decimal because it's like 0.6 repeated. So I'd have to like cut it off and round. So it makes it not accurate. So to change from a mixed number like this to an improper fraction, you take the 3 and you like the denominator and you multiply it by 1,280. So 3 times 1,280 is 3,840, and then you add the numerator. So you do like 3 times 1,280 and then plus 2, so that's 3,842. So 3,842 over the same denominator, so over 2. Oh, I don't know why I said over 2. So over 3. I didn't mean to write that there. Sorry. Some crazy stuff is happening. Okay, so I'm going to go through that one more time just because it got kind of messed up in the middle. So this is like in general to change from any like mixed number. So 1,280 and 2/3 to change that to an improper fraction. You take the denominator and you multiply it by like the whole number part. And then you take that product and you add the like numerator. So, and then that gives you your new numerator of the like improper fraction. So 3 times 1,280 was 3,840. And then you add the 2, and then that gives you the 3,842. And then it stays over the same denominator. Okay, so these are like the same thing. Just one is a mixed number, one is an improper. The improper is just a lot easier to deal with when you get like older in math. Okay, so I'm gonna go ahead and just like replace that 1,280 and 2/3 with that improper fraction. So it's gonna be 1,921 over 3,842 over 3. So now we have something called a complex fraction. You're like, yeah, no duh, it's complex. So when you have like a fraction over a fraction, remember that like fractions are dividing. So this is essentially, instead of writing it like this, I'm going to write it like a sideways division because it's numerator 1,921 divided by the thing in the denominator 3,842 over 3. And then I think that's a little bit easier to know what to do with because instead of dividing fractions, we change it to multiply by the reciprocal. So we do 1,921, we change division to multiplication, and then we flip this fraction over to get its reciprocal. So it'd be 3 over 3,842. And then now I can multiply straight across. So 1,921 times 3 is 5,763 over, this is like over 1 technically. So if I multiply straight across, it'd just be that 3,842. And then now I can divide. So things are getting better. So 5,763 divided by 3,842 is 1.5. So I can just bring this all the way down, and then as obnoxious as the whole process was, we proved that the two ratios were equal, which is what we needed to do. So we have the included angle that's congruent, and then now we have the two sides that have equal ratios. They're proportional, so that's enough to show that they're similar, but we still gotta do one more thing. Okay, so now the like a ratio between the sides is 1.5. Like we just found that it's 1.5. That number is bigger than 1, so you would have to assume that that's like the number that we would have to multiply the smaller sides by to get to the bigger side. So in other words, like if I were to take 800 and then multiply it by 1.5, that would give me the 1,200. So we got to multiply like the small sides by 1.5 to get the large sides. I have a large side and I want a small side, so I have to go backwards. So I have to take that 1,500 and divide by 1.5. So if I take 1,500 and I divide it by 1.5, that's 1,000. So after all that, it's 1,000. That's our final answer. So even though we had ugly answers, or ugly like numbers the entire time, I guess our final answer was kind of pretty. So that's nice. Okay, so biggest thing, if you want to like find missing measurements and you're not given that the triangles are similar, you just have to go out and prove it yourself, and then you can use those kind of like aspects of similar triangles, that their side lengths are proportional to find missing